By the looks of it, it is very similar to a chi-square test for independence or dependence. What do I mean by that? We have a study that measures the effectiveness of therapy. There are two types, A and B, across three different teen groups, 13 to 15, 16, 17, 18 and 19. We went and asked people after the therapy is done, did it improve, did things change? 31 here responded that therapy A worked for them, 25 responded that therapy B worked for them, and so forth. We want to verify the claim that the effectiveness is not the same among the two techniques, in the sense one of them is better than the other. How is this very similar to a chi-square test of independence? Well, if you treat that as a dependent variable, we can say that the teen groups or the effectiveness of the therapy among the three different teen groups varies as you go from A to B. That would imply that the teen groups are dependent on the therapy. Does that make sense? So, as I mentioned last time, a test for homogeneity is no different from a chi-square test for independence. This is just like a special case. So the very first step is to come up with the definition. What is the norm in this case? That the effectiveness is the same something being same simply means homogeneous. Do you see why we call this a test for homogeneity? So if we reject the null, we will conclude that the effectiveness is not homogeneous across the two different types of therapy. In other words, it's heterogeneous. We use an alpha of 0.01 which simply means that the probability of an error in rejecting the null under the given null that we've defined should be 0.01 or less. In other words, that the error has to be 1% or less. What do we need to perform the test from last time? The table of observed frequencies, the table of expected frequencies. We have the table of observed frequencies, we just have to find the table of expected frequencies. In an attempt to find those expected frequencies, we need to find the column totals and the row totals. In other words, we add the observed frequencies across the rows to get the column totals and add it across the columns to get the row total. So $56, $37, $19, When we add the row totals, it would come to 112, and it has to be the same if we add all of these, or else we made a mistake in addition somewhere, so 93, 103, 112. So that's what we have. We want to find the table of expected frequency, so how do we find the expected frequency for each cell? Suppose we want for the age group 13 to 15 under therapy A.
The row total times the column total divided by the grand total.
Row total multiplied by the column total divided by the grand total, or the total. So we observed 112 people. So for the first cell, we would look at the row total corresponding to that particular cell, multiplied by the column total for that cell, divided by 112. And repeat the same for every cell. So for the second one, you take the row total, multiplied by the column total, divided by 112. Give you a few minutes to complete that, and then we can go on from there. Okay, do we have the expected frequency? Or are we still working? What do we have for the first one? One 10.5. 27. Okay.
18.2. 9.3. 28.5. 18.8. 9.7.
Okay. The test statistic is chi-squared, and we know it has a chi-squared distribution. What is the degrees of freedom in this case? R minus 1 multiplied by C minus 1. What is R and what is C? Do we read
It's going to be 2.
2? Okay, how'd you get it?
Well, because R is 2 and C is 3.
So R is the number of rows, C is the number of columns. So 2 minus 1 times 3 minus 1, which would give us 2. And what is the test statistic? The test statistic is the sum of all O minus E squared divided by E. In other words, for each cell, we compute O minus E squared divided by E and add all of those individual chi-squares. Okay. Let's go ahead and find the chi-square test statistic. I showed you how to find it last time using the calculator by using list 1 and list 2. So I have entered all the observed frequencies in list 1, the expected frequencies that we computed in list 2. Now, I showed you how to store and get the chi-squares, but Anthony pointed this out a couple of times where you can simply use L1 minus L2 squared divided by L2 directly in the header. You have to move up to the header and hit enter, and it'll populate stuff automatically. If that makes sense. So we have found O minus E squared divided by E. Start orbiter calc. One variable statistics on list 3, and do not pick X bar. X bar is the average. We just need the sum of all individual chi-squares, which happens to be 1.7546. So we have the test statistic as 1.7546. So the test statistic is 1.7546, and we could use either the critical value method or the p-value method to obtain a conclusion. Keep in mind, a chi-square test is always a right-tail test. There is no left-tail test when it comes to chi-square. What is that shaded area? What is that amount of area? That equals alpha, which is 0.01. The rejection region is right here on the real number line. So the critical value is chi-squared 1 minus alpha, comma degrees of freedom. In my notation, I'm using chi-squared 1 minus alpha, which is the area below. How do we find the critical value? Your calculator cannot do it, so we make use of the chart to come up with the critical value. So if you're using the chart, the notation is actually chi-squared alpha, because if we look at the area above so there is that chart, so the area in the right tail, in other words, the area above the critical value is 0.01. So the table summarizes critical values for the area above. So we have to look at the column corresponding to 0.01, which is that column. And the degrees of freedom in this case is 2. We found that earlier. So the critical value is 9.210. Does that make sense? So the critical value is 9.210. 0 is right over there. What is our test statistic? Our test statistic is 1.7546, which is probably right there. Did the test statistic fall in the rejection region? No. The test statistic does not fall in the rejection region, so should we reject the null? No. If we do not reject the null, what is our conclusion? Is the effectiveness homogeneous across the therapies, or are they different? You can look at the null. They're the same. The effectiveness so there is no difference whatsoever. And the second approach is to make use of the p-value. What function in the calculator do we use to find the p-value? Chi-squared CDF. But before we get to that, p-value in this case is the area above the test statistic, because this is a right tail test. We start at 1.7546, go all the way up to infinity. And the degrees of freedom, which is 2. I mean, naturally, we should be expecting a value close to 1. So let's say if we get a value close to 1. Definitely not a small probability.
Point 4158.
0.4158 is definitely greater than the alpha value of 0.01. In other words, based on the null, based on the evidence that we've collected, if we rejected the null, the probability that we would be making an error is 41.58%. Knowing that fact, should you reject the null? Absolutely not. So it is the same conclusion as what we had earlier. Last time I showed you how this entire process can be carried out using the calculator. But regardless, we have to find the expected frequencies. Even though the calculator can be used to perform the test, we need the expected frequencies, so you should know how to compute these. But since we have a table, we need matrices to put stuff in. So press second, X in mouse, which will take us to a matrix. Go over to edit. Now that's what we had last time. Last time our table was 3 by 3. We had 3 rows, 3 columns. This time we have 2 rows, 3 columns. So, what is the first observed value? $27. The table of O's. What is the first O?
31.
31. The next one.
Okay, 15. 8. 25. 21. And 11.
Okay.
16.
Oh, 16. Okay. So that is matrix A. We need a matrix because we want to store the entire table. So second mode to exit. Press second X inverse again. Go over to edit. Now we want matrix B. And we need a 2 by 3 table. So 2 rows, 3 columns. And we need the expected frequencies. We have them over here. $27.5, 18.2, 9.3. What else do we have? $28.5. 18.8. $9.7. Yes. So we have matrix A, which saves the table of O's. Matrix B saves the table of E's. Press start. Yes.
Which button were you hitting to get to the matrix?
Second X inverse. Right next to sign. Where was I? Yeah. Start, over to tests. Which one should we use? Chi-square test or chi-square goodness or fit test? Chi-square test. So it automatically puts the observed values in matrix A, the expected values in matrix B. And there you have it. Chi-squared is 1.7570. We've got 1.7546. The p-value is 0.4158. But the accurate value is 0.4153. Yes.
After performing the chi-square test, I went back to the matrices, or matrices, I guess.
Matrices.
Matrices. And under matrix B, it no longer says like 9.3 and 9.7 under the 18-19 category. It adjusts the numbers. So it's now like 9.3304 and 9.6696. Why does it do that?
So, okay, it's a good question. So, Anthony's question was, well, these were the expected frequencies that we put in initially, but now the values changed slightly the moment we performed the test. So remember how we computed the expected frequencies manually? So when you perform the test, it would take the observed table and it automatically compute the expected values. Right? Because all we need is the row total, column total, and the ground total to find each of the expected frequencies. So if you tell the calculator, oh, my table of O's is in matrix A, table of E's is in matrix B, go ahead and perform the test. when it performs the test, it will automatically use the table of O's to compute the table of P's, which is why it's not rounded.
So theoretically, could we get by just entering a table of O's, performing a test?
I've never tried it, but you might be able to. Maybe I'll learn something new. I don't use the calculator, so I don't know. Let's try. I would expect it to give an error, but you never know. So let's delete this. Yeah, it won't let you do it. As I mentioned last time, there is another way to find, but if you can find the expected frequencies easily using this formula, why bother, doing all kinds of extra work to find those expected frequencies? That's why I didn't do it. Isn't the calculator fancy? So you can put actually any number. If it works for 0, it will probably work for anything. So if we put 0, 0, 0, 0, 0, 0, then go over to start. It did it automatically. So you can do it backwards, I guess, if you're using the calculator. If you put the expected frequencies as 0 and type in only the observed frequencies, it automatically calculates the expected frequencies for you. But don't be that lazy. I mean, this is effective and all, but don't just rely on the calculator.